All right, so I'm Erik Zuker from HNTB. I've been with HNTB about 13 years. I've been fortunate enough to wear a lot of hats while there. I started off as a bridge inspector, worked in bridge design, got to spend some time in the field looking at construction, and I'm currently helping close out some of the major infrastructure projects that we have. And throughout that time, I've tried to engage with both technology and data, specifically structural monitoring, in ways that help us better understand bridges. So I'll be speaking today. The title is longer than the topic, but on improving transportation networks using in-situ evaluation and innovative construction methods. I'll be talking about the way that a culvert was replaced under emergency circumstances using a novel approach, and also the way that structural analysis was used to analyze an entire state's worth of culverts with both finite elements and load testing. Before I do that, though, I want to step back and talk a little bit about transportation network resiliency and the specific role that bridges play in it. I have two key ideas today. The first is that rapid bridge replacement can be used as a key resiliency strategy. And secondly, that when you're considering the resiliency of an individual asset, you must consider the network around it as context to maximize resiliency. And so resiliency has become a buzzword in our industry. It was used 200 different times in the IIJA legislation. It means just about anything to anyone. It can mean something at a microstructure level for concrete, all the way up to the macro level for transportation. It's a powerful word, it's a necessary word, but it oftentimes eludes definition and especially metrics when moving between different areas of expertise. And so on the right, we see this is New York about a month ago. We had an unnamed storm come through unexpectedly, 5 inches of rain, and suddenly subway lines, highways, and even Grand Central Terminal were closed down. A tweet from the New York governor from a previous storm that year calls this our new normal. It's unfortunate, but we have frequent reminders of why these are so important, these conversations are so important. And so, from my perspective, bridges play an outsized and maybe singular role in transportation network resilience. I'm of course biased being a bridge engineer, but I think we have to look no further than the state of Vermont in 2011. When Hurricane Irene went through, a landlocked state was affected so deeply by a hurricane that 300 bridges were taken out of service, and they had to airlift food to communities. We know that bridges are bottlenecks even on our good days, so let alone our bad days. They're oftentimes the most fragile and the first to fail when flooding occurs, and they're the hardest to retrofit on the front end and most expensive to replace and most timely to replace on the back end. So the design process has three main phases, really boiling us down to the simplest terms. We have the demand, of course. We engineers can spend our most time and expertise looking at materials and detailing and sizing of elements. And then, of course, it's an iterative process between steps 2 and step 3 as we look at capacity from both the code and finite elements. Steps 2 and 3 are largely deterministic. If A equals B, B typically equals A, whereas step 1 is highly probabilistic. If steps 2 and 3 are going to your accountant, step 1 is going to the casino. So the problem becomes, what happens when those probabilities change so significantly? The photo on the left was taken from Hurricane Harvey, which went through Texas and Louisiana in 2017. In certain places, the rainfall was a 250,000-year event. Not a 1,000-year storm, not a 10,000-year storm, but a 250,000-year storm. And that's according to NCHRP report 975. Now I'm going to say two things that are controversial. Number one, the rate of change for the demands far outpaces our ability to codify and incorporate this into our design process. And the second controversial thing is we can't engineer our way out of this. If you show me a bridge that can withstand a 250,000-year event, I will show you a bridge that is far too expensive to be practical. And so the code is certainly the minimum. It's our imperative as engineers to meet the minimum code requirements for local, state, and national. But I believe as engineers, it's our job to now work more with the owners and agencies, help them understand what are the trade-offs and the uncertainties in the future so they can best balance the risk versus the cost of mitigating. And I'm not a climate scientist, it's not my area of expertise, but I want to go just a little bit beyond the anecdote I just shared and show some actual data. Both of these plots are from the EPA, and both are actual data as opposed to projections. On the left, we see more than 100 years worth of extreme rainfall data with a distinct increase in the past 30 years as far as rainfall intensity. On the right, we see river levels between 1965 and 2015, And we see a significant increase, meaning the blue triangles facing up, in the Northeast, the Midwest, and the Northwest. It's my conclusion from this data that the inland flooding due to extreme rainfall will be a significant threat for bridges in the future and already. Now, it seems like some sort of general unspoken rule that whenever you say the word resilience in a presentation, you have to show this graphic, and so I'll get it out of the way now. Most of you are familiar, but I'll walk through it quickly. A system has a certain level of functionality, and after an extreme event, that functionality is lost and then restored. We spend a significant portion of our time, maybe most of our time, looking at ways we can shallow that curve, the resist piece, by hardening assets and making them more resistant. We spend a very limited amount of time working on the restore piece, ways that we can shorten the length of that curve and reduce the time that piece is out of service. And that's how I feel bridge replaceability can serve and engage. Now, why do I have leaves falling on the right? Is it because we're in New England in the autumn time and that's just what people do is look at leaves falling? It's actually because on the statistical side, I find that analogy is much more powerful than equations. If I'm standing in the woods and a breeze picks up in autumn time and I look up at a single leaf, what are the odds that that leaf will fall? Relatively small. What are the odds in the same circumstance if my field of vision is thousands of leaves and I look at all of them? Very high that one or more of those leaves will fall. It's the same thing with bridges. Because the rainfall is so hyper-localized and extreme in certain little pockets, the probability of any given bridge failing is relatively low, while the cumulative probability that at least some of the bridges will fail is high. And so vulnerability assessments are being performed by states across the country. Many have finished their first pass, and most are, or some are, other ones are still engaged. The typical playbook involves the two topics on the left. If a bridge or an asset is vulnerable, we either replace it with new construction or we replicate it with specific resiliency measures, in this case, stone to mitigate any scour concerns. Now, these are certainly prudent, and it's absolutely the right way to prioritize our assets. However, this process, by any measure, will take significant resources and years, if not decades. And so what I'm proposing is that in the meantime, while all the unaddressed assets still are in service and out there, before we have time to replace them, we look at ways to shorten and reduce the length of time it takes to get critical assets back online. What are ways we can be proactive now to make our worst day less bad? I find it very interesting that 89% of the bridges in this country have a longest span of 100 feet or less. What if there were solutions that we could utilize to solve 9/10 of our problems as they arise? Now, of course, we all know as bridge engineers, those of us in the room, that it's not this simple. When I use this slide and this graphic with the non-bridge engineering community, they figure let's just make a universal bridge, cut it down to size, and we have problem solved. There's people in this room who have dedicated their lives to the even narrow bands of complexity of bridges themselves. So if we can't make a universal bridge, what can we do? Well, we can group the inventories that we have and look for ways that we can solve groups or classes of problems within an entire DOT. We can look at concept designs built ahead of time, so we're not starting at square one, but maybe square 10. And that way things like geotech design and substructure can get started almost immediately. We can build contractual mechanisms in place so that we're not fighting restrictions or bureaucratic processes when these occur. And finally, we can procure strategic material ahead of time so that it's not only ready to go, but that we're not paying premium prices and immediate rush shipping for that time. Now, I've talked to stakeholders across the country about these topics, and by and large, they think I'm talking about ideas that are pie in the sky, too optimistic or too naive to actually work. So I want to talk about a case where we actually use many of these methods. In 2021, Hurricane Ida went through New York, setting record rainfall, and shortly on the heels of Hurricane Henri, which also set rainfall records just before that. There was significant flooding, and numerous infrastructure was damaged. The photo on the left was used by numerous local news organizations as their sort of header photo. It kind of became the iconic photo for that storm. And it just so happens that center stage of that photo is myself with a backpack. I was one of the emergency inspectors deployed to this site, one of the worst damage in the entire city. We see people walking below the railroad where gravel was only a few days before. And so when people ask why I'm so passionate about bridge resiliency and extreme weather, this is why, having seen this firsthand. It laid three things bare for me. Number one, extreme weather has very real and tangible impacts on our infrastructure and will continue to do so. Number two, hidden vulnerabilities lie in our system without being realized. This culvert had been fine for 110 years with almost no maintenance and was not on anyone's radar for any specific concern. And yet this is the one that failed. And number three, the way that cascading impacts occur within a network. A span less than 20 feet long suddenly was impacting 30,000 commuters. And so the view on the right also shows the steel prices at that time. Unfortunately, Hurricane Ida struck at the worst possible time for steel prices, not only price, but also availability. So what were our options? HNTB was engaged for the emergency redesign of the structure. We initially talked to culvert manufacturers. They were so far in back order because of supply chain issues, they couldn't be of any help in the time frame we needed. We looked at a steel through-girder solution, the typical railroad play, but that didn't work either because of the steel issues I just mentioned. So what did we do? We were able to utilize a filler beam solution that uses relatively shallow W sections, closely spaced side by side, and a concrete slab that goes almost all the way to the bottom of that I section. This leverages the best properties of both concrete and steel, and has numerous advantages that were good for this specific site case. I mentioned the steel shortages and that issue. There's limited site access, and so getting heavy lifting equipment to the site was not possible. All we had to lift was the steel beams themselves. We had to deal with adjacent train traffic, which made logistics and form work more difficult. And we also had, we wanted to increase the hydraulic opening, so the shallow section depth allowed more water to fly through. This is a picture of the nearly completed bridge with the abutment shown as well on the left, and the completed bridge on the right. We also had the advantage that our W sections, even those that we selected, were not available. And so we had our contractor walk around the yard with his fabricator and find the W section that worked. Because there's essentially no connections on the steel beams, they just sit on the bearing and are held together by the concrete around them, we were highly flexible on what pieces we could use. They suggested a few W sections, we ran the numbers, and were able to confirm that they worked. Amazingly, just as this project was being wrapped up, another rail client in the New York area had a truck strike that was so significant that it took the bridge out of service, one of their main lines. We again deployed the same tactic, filler beam solution. The shallower depth meant the trucks had greater headroom, and by the way, I wouldn't want to be the truck that drove straight into all these beams. And so before I wrap up this half of the presentation on bridge replaceability, I want to talk a little bit about risk. Now, it's dangerous to boil any entire field of study down to a single equation, especially one with two variables, but I'm going to try. Risk is essentially the likelihood that something happens and the consequence of it actually happening. And so I place those as the X and Y on this plot. In the top left, we have the reliability space. You could argue that asset management is here. You could argue that bridge preservation is here. These are things that are likely to happen, but are relatively low consequence if they do. This is your deck deteriorating. Likely going to happen at some point, but not a life safety issue unless it's unaddressed for a long time. On the bottom right, we have the vulnerability space. This is extreme design. Earthquake, ship impacts, unlikely to happen, but very significant and life safety consequences if they do. What I'm seeing more and more is these two areas are joining up together, not least of which because the extreme weather that we have is no longer becoming low probability, but actually increasing in probability while maintaining the same level of severity. While we typically think of life cycle analyses and vulnerability analyses on separate tacks, I believe it's becoming more important with the limited resources we have and the aging stock of infrastructure to assume and look at those two things side by side. And so now I want to switch gears to the network piece. There are individual assets that we're evaluating resiliency for, and that's a typical thing that many DOTs are doing. But without looking at them in the context of a network, we can't effectively review them fully. Now, we have experts, many of them in this room, who know the way that assets behave on their own. And separately, we have experts who know how networks work. Traffic modelers, freight planners, emergency operations specialists. There's a very limited framework or vocabulary between these two groups. And while there are great examples, it's rare that they have an effective conversation between them. I don't see this so much as a problem as a massive opportunity space for our industry to do better in the future. Now, we're all familiar with what happens when bridges are taken out of service. On the left, we see the tragic event on I-95 with a truck fire in Philadelphia this summer. It had massive implications for the I-95 corridor, and amazingly was actually put back online within 12 days, albeit without the underpass there. On the right, we see the Hernando de Soto Bridge, where I-40 crosses from Memphis into Arkansas. This bridge, with a single member, a single fractured bottom chord, suddenly had impacts that were so dire that 60% of the westbound lanes out of Memphis were taken out of service. Massive local implications for traffic congestion, but also significant freight implications that actually changed the freight patterns for the entire country. And so networks behave in different ways. Sometimes you have a chain. Think freight rail between Texas and California. Only one or two routes, and so every single bridge is can't lose. On the other hand, we have things like networks that are like webs. Think the cornfields of Iowa, where it's a 1 mile by 1 mile grid, and any single intersection is not all that critical. Part of the problem is that a lot of times we evaluate and we prioritize these based on a criticality factor. And I beg the question, criticality to who? If I live on a local street and that bridge is the only way I can get into town, that's a very critical bridge. This also begs significant questions on equity side of things. If there are underserved communities, both in the rural or urban context, we have to make sure that our criticality assessments don't disproportionately affect that. What has changed when it comes to bridges and networks? Bridges have been a part of networks since the dawn of time. I would argue three things. Number one, our networks are becoming more complex and interconnected, especially with intermodal travel for freight. Number two, extreme weather that we've talked about is putting a greater duress on these networks and how they behave. And number three, our ability to look at data and to use it effectively has grown significantly. I don't have time to go into all four of these in depth, but these are four projects with HNTB that I've led to utilize data and technology to better understand bridges and the way that they fit within a network. On the top left, we were able to take specific traffic from Google Maps and actually build a database off of it to track changes over time. On the bottom left, we've deployed wireless and cloud-enabled monitors to keep an eye on specific bridges as how they perform during extreme events. On the top right, we see tens of millions of lines of weight and motion data represented. We actually, for this given facility, there's weight and motion in both directions on the bridge. And we found that because of local congestion and tolling perspectives or prices, we actually found that one direction of the bridge saw 3 times the overweight load of the other direction. We're essentially running a bridge preservation experiment in real time. And the bottom right is the precipitation data. There's a publicly maintained data set of precipitation that is for the past 25 years down to 5-minute increments, and for the entire continental US down to 1 square mile. Our ability to understand and quantify and even look forensically at bridge failures in the past has never been greater than it is right now. All of these processes have been enabled by open source programming languages, data visualization, and utilizing cloud resources to handle massive data sets. And so on the freight side, what does freight do to our network? Well, with the advent of e-commerce, with the addition of significant warehouses, we see that freight can actually change at the speed of light compared to the way we can adapt our methodologies and our structures. What used to be a sleepy back road with the addition of a warehouse can actually become a main freight corridor, seeing a 100x increase in the heavy trucks on that load. When a truck driver gets off a highway, which of these 2 signs are they going to see? It would likely be governed by the bridges and the culverts along that route. And so when we talk about robust corridors, I'm talking about robustness not only and not resilience not only to extreme weather, but the resilience to be able to handle the freight along that route. And I believe that falls to bridge engineers to help other decision makers truly understand what those are. This example is perhaps too cartoonish to be useful, but let's give it a try. Town on one side of the river and hospital on the other. A river going between with only 3 bridges across that are identical. If that river sees a major flooding event, all 3 of those bridges are vulnerable and to the same degree. And so what looked like a very redundant and probably safe route may actually get wiped out at the same time, which just demonstrates the importance of having hardened corridors to be able to use with safety, especially to medical critical facilities like this, and also the reason that we can't use detour length as a sole criteria for looking at which bridges are most critical. And so I make an argument that bridge engineers have a unique role to play in this, especially in helping other decision makers make the best decisions they can. So the top left is an inspection report, and this is a small screenshot, and it's actually taken from 40 straight pages of these tables. Who but a bridge engineer could understand these, and who but a bridge engineer would want to understand these? And these are critical, mission-critical documents for understanding how vulnerable a bridge is and when it should be replaced. On the bottom, we see a retrofit of one of the entrance ramps to the Brooklyn Bridge. When you're looking at asset management life of pavement, there's typically a pretty consistent number. X number of years for this specific corridor, we have to replace pavement, and that's our best use of net present value dollars. Bridge retrofits are truly a choose-your-own adventure. There's different materials we can use, different methodologies we can use. We can map out certain ways we can manage risk, and we can even coat in a certain way to even give additional service life. These are decisions that others do not have the ability or wherewithal to make these, and so really I believe it does fall to us, because with IIJA and the once-in-a-generation funding that we have, we're setting the cadence for our entire industry. And so my last case study is the culvert example with load rating. And I should say this is Dr. Foden's work, so any questions specifically on this task, I'm going to deflect to him. He was supposed to be my co-presenter, but as he mentioned, due to outages people, I stepped in to present his portion. And so ultimately, a new load rating method was necessary, and so many of the culverts in a whole state did not rate appropriately. And so there was concern they would have to post these culverts, which would have potentially paralyzed the entire freight network if certain trucks can't go over in major routes. And so the problem is these culverts have been in service for numerous decades with almost no signs of wear. So the suspicion was they actually were fine, but given the new methodology, that couldn't be proven. And so what Dr. Foden did was he utilized not only in-situ testing and load testing on the bridges themselves, but built finite element models, calibrated those to verify assumptions and remove conservative assumptions that were put in place to better refine the analysis. And the conclusion was ultimately that most or all of the culverts that had been suspect actually were found to be passing. And so my presentation has been more context than case study, so I appreciate you sticking with me. I hope it brings a little bit different perspective on the bridge resiliency conversation, moving from the asset up to the entire network. The work, a lot of people in my group, in my bridge group, are really clamoring for, can I work on the next big signature structure? What's your long span bridge and can I work on it? What I see as equally challenging, complex, and interesting is networks of small bridges and how they interact with one another during these extreme events. And so I hope you'll at least consider my two main ideas. The bridge replaceability can be a key factor in resiliency metrics, and that we can utilize assets at a resiliency at an asset level all the way up to the network. Thank you.